Welcome to the Deep Dive, the show where we take complex source material, technical reports, engineering blueprints, high-level analysis, and distill the absolute critical insights you need to know.
Today, we are immersing ourselves deep in the realm of heavy-duty commercial vehicles. We're tackling a really fascinating paradox at the intersection of structural engineering, vehicle electrification, and hard-nosed profitability.
Specifically, the cement mixer truck.
Exactly.
That's right. So forget the sleek consumer electric vehicles for a minute. We're talking about the absolute backbone of global infrastructure.
Yeah.
Our source material is a comprehensive engineering blueprint, a systems engineering roadmap, really, for designing the body and protective systems for a hybrid cement mixer.
And this isn't just any hybrid. It's a P2 hybrid system on a 24-volt, 400-volt platform. And this deep dive isn't just about, understanding how they bolted on a battery. It's about solving a fundamental business and engineering conflict. The team's mission here was to build a complete capability from scratch, to design these body components to meet the highest standards for power, safety, and durability in, well, the most brutal operating conditions imaginable.
So let's start there. Why even hybridize a cement mixer? I mean, it seems a bit counterintuitive. These things are all about massive diesel engines and a mechanical power takeoff, a PTO, to keep that huge drum spinning.
Exactly. And that drum has to spin constantly, whether the truck is on the highway or more often just sitting idle for hours, waiting to be filled, stuck in traffic, or at the construction site.
And that traditional diesel PTO is just burning fuel the whole time.
An immense amount of fuel. It's profoundly inefficient. It wastes diesel, creates noise pollution, churns out emissions right where people are working.
So the hybrid solution, the electric PTO, is designed to fix that specific problem.
It is. The P2 architecture, with an electric motor between the engine and transmission, and this ePTO, allows for zero emission weighting. The truck can be completely silent, engine off, but the drum keeps turning. It's a huge win for fuel economy.
Okay, so let's unpack the core problem this whole blueprint had to solve. You had all this heavy electrical gear, the battery, the motor, the controls to save fuel. But that very system creates what the report calls the weight paradox.
And that paradox is the absolute core tension of the entire project. The weight you add for sustainability directly threatens the vehicle's profitability.
Because in this business, weight is money.
It's the most payload-sensitive business in trucking. Every single kilogram you add to the truck's empty weight is a kilogram of concrete you cannot legally sell and deliver.
So that lost payload is lost revenue.
Precisely. If the hybrid system adds, say, 500 kilograms and you can't offset that, the customer just can't make their money back. The tech is pointless if it destroys the total cost of ownership, the TCO.
So our mission for this deep dive is to explore the blueprint they developed. It's a systematic counteroffensive against weight, but it's combined with the extreme safety requirements you need for high-voltage systems in, well, the world's harshest operating environment.
It's engineering innovation driven by pure economic necessity.
So moving into our first section, we have to look at the numbers, the cold, hard numbers that define this challenge. We're calling it weight versus wealth, the TCO imperative. Just how big is this weight penalty we're fighting?
The initial breakdown is pretty stark. It's a real engineering reality check. And these are non-negotiable weight additions, dictated by physics and current battery chemistry.
Okay, so lay it out for us. Where does all this weight come from?
Well, the biggest piece of the pie is the high-voltage battery pack. For this kind of stop-start operation, you're looking at something between 30 and 60 kilowatt hours, and they're using LFP chemistry.
Lithium iron phosphate.
Right. And LFP is crucial here because it's safer. It has superior thermal stability and a longer cycle life. It's just more robust for this kind of work.
But there's a trade-off with LFP, isn't there?
There is. It's less energy dense than, say, the NMC cells you find in a lot of passenger EVs. So to get the energy you need, the pack has to be physically bigger and heavier. For this size, you're adding 350 to 450 kilograms right off the bat.
Just for the battery.
Just for the battery. Then you add the components that do the work. The motor, the reducer, the clutch for that P2 setup. That's another 120 to 180 kilograms.
Okay.
And on top of that, you've got all the power electronics, the inverter converters, all the high voltage orange cables, the cooling loops. That's another 40 to 70 kilograms.
And then the part we're really digging into today, the the structure itself.
Exactly. The high voltage structural protection, the beams, the shields, the mounting brackets. It all has to be over-designed to meet global safety standards like ECE R100 or China's GB 38031. Even before you try to optimize it, that's another 60 to 100 kilograms.
So what's the total initial hit?
You're looking at a range of 570 kilograms up to 800 kilograms. And for bigger systems, that can easily go past 1,100 kilograms, over a metric ton.
That is just a staggering amount of mass to overcome, especially when the whole point is to be economic. And this is where it gets really interesting, because that weight translates directly into currency.
It's the engineering team's core mandate. It's not just about safety, it's about solving the customer's TCO problem. You add 600 kilos, the customer buys the diesel truck. Every time.
So let's quantify that. Let's use the TCO analysis from the source material. It's based on a pretty conservative scenario, right? Losing just 300 kilograms of payload per trip.
Yes. And the operational metrics are standard for the industry. A truck runs about 10 trips a day, works about 300 days a year. And concrete is priced conservatively around 100 RMB per ton.
Okay, so you run those numbers. 300 kilos, 10 trips a day, 300 days a year.
And the annual revenue loss is calculated to be approximately 90,000 RMB per truck per year.
8,000 RMB every year, just from 300 kilograms. That figure is the economic engine driving this whole project. If you don't recover that 300 kilos, the hybrid program is a failure.
It's non-negotiable. The mandate is clear. Every single kilogram of structural weight you can cut translates directly into the customer's cash flow. It's at a literal exchange rate. Steel for money.
So, with the stakes that high, what were the targets? What was the goal for this counteroffensive against weight?
The primary target was ambitious. They had to offset at least 60% of that hybrid weight penalty.
60%.
And that was broken down into very specific goals. A structural and subframe reduction of at least 300 kilograms, that's the magic number for the revenue, and then another 120 kilograms from non-structural components.
How do you even do that without just throwing, I don't know, super expensive carbon fiber at it? That would just destroy the TCO all over again.
They established a systematic approach, a lightweighting matrix with 3 paths. But it all operates under one guiding principle, maximizing structural efficiency.
Structural efficiency. Okay, let's unpack that. What does that mean in practical terms? Kilograms per kilonewton.
It means you're not just looking for the lightest material, you're looking for the design and material combo that gives you the most load-bearing capability, the kilonewtons, for the least possible mass, the kilograms. It's about smart design, not just expensive materials.
So it's about being clever with the geometry.
Exactly. Think of a spider web versus a solid steel block. The web is far, far more efficient at managing load for its weight.
Okay, so what are the 3 paths in this matrix?
Path 1 is structural optimization. This is pure design intelligence using CAE tools. You're aiming for a 10 to 25% reduction just by taking material away from places where it isn't doing any work.
Path 2 is material substitution.
Correct. This is where you move from standard high-strength steel to ultra-high-strength steels, and very carefully using aluminum alloys. The strength goes up so the thickness can come down. This offers a huge potential reduction, 15 to 40%. But
it's more expensive and it introduces new problems like corrosion.
Which we'll get to. And path 3 is process innovation. Using advanced manufacturing like hydroforming to create shapes that are inherently stronger and lighter than anything you could stamp or weld. That gives you another 5 to 15%.
So by combining all 3, they can systematically chase that 60% target.
That's the blueprint.
Okay, so we've set up the weight problem and the strategy. But before we can start taking weight out, we have to talk about putting it back in the most critical place, the safety cage. This is section 2, protecting that high voltage battery.
This is the first non-negotiable hurdle. If you can't prove the high voltage system is safe, the project just stops. The whole design philosophy for this safety cage has to satisfy 3 functions.
What are those 3 functions?
First, energy management, so absorbing impact energy. Second, anti-intrusion, which is blocking things from actually piercing the battery. And third, load path control, which is about diverting crash forces away from the battery and through the main chassis.
And all of this has to meet or really exceed standards like ECE R100 and the very tough Chinese standard GB 3803 Hoi. So let's start with the first threat, side impact.
Right. The battery is often mounted on the side of the truck along the frame rails, which makes it incredibly vulnerable. The solution is a dedicated side impact beam frame, and the material choice here is critical. Thermal-foamed boron steel.
Boron steel. I know that's used in high-end cars for safety cells. It's really strong, but also expensive.
It is, but it gives you the best strength-to-weight ratio for this job. We're talking a yield strength of 950 to 1100 megapascals. Standard steel is maybe 250.
So it's 4 times stronger.
At least, which means you can use a much thinner, lighter part to do the same job, which helps with our overall weight problem.
And how is the beam itself designed for efficiency?
It uses a closed hat section, basically a box shape for maximum rigidity. But the most important detail, the real intelligence, is the crush box at each end where it bolts to the chassis.
Wait, a crush box. If you're trying to save weight, why add a separate component? Why not just make the main beam thicker?
Because that's the fatal flaw. The goal isn't just to be strong, it's to manage the energy. The key metric is limiting intrusion to less than 100 millimeters. To do that, the beam and the crush box have to absorb at least 60% of the impact energy.
So the boron steel beam provides the anti-intrusion strength, and the crush box acts like a shock absorber.
Exactly. The report has this stark warning. If you just use a single thick, rigid plate, it doesn't absorb the energy. It transfers the entire peak force instantly into the battery case. The cells crush, short circuit, and you get an immediate fire. You have to design for controlled failure, not absolute rigidity.
That's a critical distinction. Okay,
Yeah.
what about underbody protection? This truck is not on a smooth highway.
No, it's in a nightmare environment. You've got high-speed stone impacts, rocks being kicked up like projectiles. And the new draft of the GB standard introduces a test for continuous scraping.
Continuous scraping.
Yeah, simulating the truck getting high-centered on an obstacle, dragging the battery shield over rocks or rebar. To handle both, they designed a hybrid underbody shield, a multi-layer solution.
What's in this hybrid shield?
The base layer is 3 millimeters of high-strength steel for basic puncture resistance. But the key layer on top of that is a 2.5 millimeter aramid fiber composite.
Aramid fiber. So we're talking about the same stuff used in body armor.
That's the perfect analogy. It has incredibly high specific energy absorption. It's designed to dissipate the energy of that sharp, high-velocity impact and stop it from getting through. You get more than 3 times the anti-puncture capability.
And the weight penalty for that.
It's remarkably low, only about 18 kilograms. That's a perfect example of structural efficiency, a tiny weight cost for a massive safety gain.
Now let's shift to a threat that's unique to this vehicle. Vibration fatigue.
Yes, this is where the truck's own job becomes a danger to itself. The constant rotation of that massive, heavy drum of wet concrete creates a very specific, low-frequency torsional vibration. It's in the 3 to 5 hertz range.
And if that matches the natural frequency of the battery mounting brackets,
You get resonance, catastrophic resonance. The brackets start oscillating violently, and you get fatigue cracks in the welds, the bolt holes. The whole thing just tears itself apart over time.
so the solution is modal separation. You have to design the bracket's natural frequency to be nowhere near that 3 to 5 hertz range.
Exactly. The target is to get the first-order natural frequency above 15 hertz. The blueprint actually recommends aiming for over 35 hertz for an optimal safety margin.
How do you even test for that? A static strength check isn't going to cut it.
Not at all. It's totally insufficient. The mandate is for a full time domain vibration fatigue analysis using tools like ENCODE or FEMFAT. They run a simulation of the vehicle's entire 10-year life on terrible roads to make sure the stress in the welds never gets close to the fatigue limit.
And finally, under safety, we have to talk about sealing, the IP69K mandate.
The environment is just brutal. You've got corrosive concrete dust, and then every day the truck gets hit with a high-pressure, high-temperature washdown. We're talking 80 degrees Celsius water at 1450 psi.
So IP69K is the highest possible rating for that kind of abuse. How do you achieve it?
Well, you need perfect seals, often using something called FIPG, or form-in-place gasket, which is a liquid that cures into a perfect seal, or a dual-layer design. But the really clever bit is the ePTO breathable valve.
A breathable valve. If you want to seal it, why would you let it breathe?
It's to prevent what engineers call the straw effect. As the battery heats and cools, the air pressure inside changes. If the pressure drops, it creates a vacuum that can literally suck water in past even the best gaskets.
So the valve lets the air pressure equalize without letting any water in.
Precisely. It lets air molecules pass but completely repels water. It's a pressure regulator and a water shield all in one.
And what about the worst case scenario? An internal battery fire, thermal runaway?
The standards, both ECE R100 and GB38031, demand a 5-minute warning before any fire or explosion to let the driver escape. The strategy is twofold.
Passive and active.
Exactly. Passive insulation, using materials like aerogel or mica between the cells. Aerogel is an incredible insulator. It can stop that heat from spreading from one cell to the next, slowing down the chain reaction.
And the active part?
Active venting, you design special anti-explosion valves that, when the pressure spikes, open up and direct all the hot gas, smoke, and flames safely downwards and away from the cab, the tires, and the fuel tank. It's a multi-layered defense designed to manage a catastrophe.
That deep dive on the safety cage really shows how structure is insurance. But we also said weight is profit. So now we move from safety to the core supporting structure, the subframe, which is what actually carries the payload.
This is where the engineers earn that 90,000 RMB back for the customer. The subframe connects the main chassis to that huge mixer drum. It's all about durability and payload.
And the first step is topology optimization. What's the old way versus the new way here?
The old way was simple. You just used thick, heavy, rectangular steel tubes. Easy to get, easy to weld, but massively inefficient. You have material everywhere, even in places where there's almost no stress.
And topology optimization flips that on its head.
Completely. You use CAE software, you tell it where the loads are, where it needs to be attached, and you give it a goal, like maximize stiffness. The software then runs millions of iterations, digitally carving away any material that isn't doing critical work.
So you end up with these very organic, almost bone-like structures instead of a simple blocky beam.
Exactly. It's like mimicking nature. You can eliminate 30 to 40% of the low-stress material. For a huge component like a subframe, that's a weight reduction of 80 to 120 kilograms just from smart design.
Wow.
And you get a secondary benefit, better fatigue life, because you're eliminating a lot of the welds that create stress concentrations.
Now, there's another challenge here, flexible mounting. The report says the chassis itself is actually weaker because they had to cut into it to fit the battery pack.
Right, you can lose 15 to 25% of your local torsional stiffness. So now you have a problem. You have this super stiff, optimized subframe bolted rigidly to a now slightly more flexible main chassis.
And when the truck twists on an uneven construction site,
Crack. You get massive stress right at the connection points and something will fail.
So the principle here is counterintuitive. The subframe shouldn't try to reinforce the chassis. It needs to, coordinate with it.
It has to coordinate deformation. The solution is brilliant. You introduce sliding mounts or spring-loaded connections. They allow the subframe to move just a tiny bit relative to the main chassis, releasing that dangerous torsional stress before it can build up and cause a crack.
It's like letting the structure breathe instead of fighting itself.
It's structural tolerance. It's a critical design principle for any heavy truck that goes off-road.
Which leads us to a fascinating chemistry deep dive, connecting dissimilar materials. We're using aluminum to save weight, but we have to bolt it to a steel chassis.
And that introduces the terrifying threat of galvanic corrosion. Aluminum and steel have about a 0.8 volt potential difference,
Which, in the presence of an electrolyte,
creates a battery. And what's the perfect electrolyte on a cement mixer?
the concrete slurry itself, it's wet, it's conductive, it's highly alkaline.
It's the perfect storm. The concrete slurry has a pH of 12 or 13. When you have aluminum, the anode, connected to steel, the cathode, in that electrolyte, the aluminum just dissolves. It sacrifices itself rapidly, and your structural component fails in months, not years.
So how do you stop it?
Solution 1. Physical isolation. You have to break the electrical circuit. Wherever aluminum touches steel, you use non-conductive insulators, gaskets, sleeves, washers made from something like fiberglass reinforced nylon.
So you're putting a plastic barrier between the two metals.
A very strong, chemically resistant plastic barrier. And solution 2 is to use modern joining techniques. Instead of just bolting, you use structural adhesive bonding.
The glue itself is an insulator.
An excellent one, as long as the bond line is thick enough, say over 0.3 millimeters, you combine that adhesive with self-piercing rivets, and you get a joint that's strong, fatigue-resistant, and completely sealed off from that corrosive slurry.
The rule is no bare metal-on-metal contact.
Absolutely not. And then you have to protect the steel itself. The whole paint system has to be alkali resistant.
No.
The e-coat needs to be thick, especially on the edges, and the total paint thickness needs to be at least 80 micrometers.
And there was one final detail about manufacturing.
Yes, all welds must be sealed twice. Welding burns off the protective coatings and creates tiny cracks where the slurry can get in. You have to seal them with a heavy-duty sealant to stop the corrosion from starting from the inside out.
Okay, so we've optimized the safety cage and the subframe. Now we get to section 4. Chasing the rest of the weight targets and meeting some demanding new safety standards for the cab and other external parts.
This is where we go after those quick, high ROI wins to hit that secondary target of reducing weight by another 120 kilograms. We're talking about non-structural material substitution.
So swapping heavy steel parts for lighter polymers where it makes sense.
Exactly. For example, you replace the heavy steel front bumper with SMC sheet molding compound. That's a 40% weight reduction right there.
What else?
The mudguards and fender extensions. You switch from steel to LFT long fiber thermoplastics. That's a 50% weight cut. The footsteps, you go from steel to aluminum extrusions, you save 30%.
Individually, they're small, but they all add up to that 120 kilo target.
They do. And the commercial side of this is fantastic. The total added cost for all these changes is less than 5,000 RMB per vehicle. But because you're avoiding that 90,000 RMB revenue loss, the ROI on these parts is less than 6 months. The lightweighting pays for itself almost instantly.
I love that. Now, what about what the report calls free lightweighting aerodynamics? This feels like a stretch for a big, boxy cement mixer.
You'd be surprised. On the highway portion of its duty cycle, aerodynamics can account for over 35% of its energy use. So any reduction in drag is a direct saving in fuel or electricity. It's like reducing the physical weight for free.
So what are we talking about here? Big, sweeping changes.
Not at all. Simple things. An optimized air deflector on the cab roof, maybe some side skirts. These can reduce the drag coefficient by 3 to 5%. That translates to a 2 to 3% reduction in energy consumption over a year. The cost is tiny, the savings are real.
Okay, now we have to talk about protecting the driver. The ECE R29 Revision 3 cab safety upgrade. This is the new gold standard.
It is, and it's much tougher. It introduces a new A-pillar impact test, and critically, it upgrades the roof crush test. The roof now has to withstand 98 kilonewtons of force. That's almost 10 metric tons pressing down on it.
So how do you meet that standard while still trying to save weight?
You can't just add more thick steel. You have to use smarter, stronger materials in the critical load paths. So again, we're using ultra-high strength boron steel, over 1,500 megapascals in the A-pillars and the rocker panels. This lets you actually reduce the thickness while making it much stronger.
And manufacturing processes play a role here too.
A huge role, using hydroforming to create the A-pillars. Instead of welding pieces together, you use high-pressure fluid to form a single, seamless part with a variable cross-section. It's lighter, has no weak points from welds, and is incredibly strong.
There's a fascinating concept in here called the wisdom of retreat. It sounds very counterintuitive for safety.
It is. It's a dynamic approach to managing energy in a severe frontal crash. Instead of making the cab suspension mounts totally rigid, you design them to break in a controlled, predictable way.
You want them to break.
In a severe crash, yes.
Mm-hmm.
Because when they break, it allows the entire cab to shift backward by 15 or 20 centimeters.
What does that do?
It absorbs a massive amount of kinetic energy, and, crucially, it lengthens the time of the crash event. By spreading that deceleration out over a longer period, you dramatically lower the peak G-forces on the driver. The cab is, in a sense, taking a step back from the punch.
That is clever. It's safety through controlled movement, not just brute force.
Exactly. And finally, there's the external protection, the rear underrun protection device, or RUPD.
The bar at the back that stops cars from sliding underneath.
Right. And the new standard, ECE R58 Rev 3, has massively increased the force requirements. The offset test point now has to withstand 180 kilonewtons, 18 metric tons of force.
So how do you build a bar that can take that kind of hit without weighing a ton itself?
Again, it's about smart materials and smart design. You have to use 700 megapascal class high-strength steel. The main crossbeam has to be a closed box section, not a simple C-channel. And the arms connecting it to the chassis need to have controlled crush zones so they absorb energy instead of just ripping off the frame.
So we've dissected the entire engineering blueprint, from the safety cage to the subframe, the corrosion, the cab upgrades. Now we get to the final gate, validation, the engineer's bottom line.
This is critical. The blueprint says compliance isn't the end, it's the starting line. Before you spend millions building a physical prototype, the virtual validation the CAE has to pass. It's called the digital gate.
And the rule is absolute. No CAE convergence, no prototype. So what's on that mandatory checklist?
There are 4 key virtual tests. First, a full load rollover to make sure the cab and the battery containment hold up. Second, a side pole impact on the battery zone to prove that boron steel cage really works.
And third, one that's very specific to this truck's life.
Yes, the pothole road impact simulation. This is a brutal fatigue test on the subframe, the flexible mounts, everything. It proves that our coordinate deformation strategy actually works over a full lifetime of bad roads.
And the last one.
An emergency brake in a turn. This tests the torsional rigidity of the whole integrated system, chassis, subframe, and the heavy sloshing load of the drum under the most extreme handling maneuvers.
So this digital rigor is what guarantees the physical truck will meet all those complex requirements for power, economy, and safety, including the ISO 26262 functional safety standard.
It guarantees robustness. You simply cannot balance the weight target, the safety mandate, and the durability requirement without this level of advanced simulation before you ever cut a single piece of metal.
Which brings us to the engineer's final principle, the bottom line that really ties this whole deep dive together.
The core philosophy is stated very clearly. On a hybrid cement mixer truck, weight is profit and structure is insurance.
I love that.
You can and you must negotiate every single gram of steel for the sake of that 90,000 RMB. But you can never, ever compromise on high voltage safety.
It's a perfect summary of balancing commercial reality with absolute safety.
Yeah.
What an incredible journey. We've seen how this systemic thinking let engineers tackle that central weight paradox and turn a safety requirement into a catalyst for total vehicle efficiency.
We really covered the three pillars of the blueprint. First was systemic lightweighting using optimization and smart materials to reclaim enough payload to give the operator that 90,000 RMB a year in value. Second was shield-level high-voltage protection, designing that boron steel cage and that aramid fiber underbody shield to exceed global standards.
And third was full life cycle durability, managing corrosion, mitigating that unique vibration, upgrading the cab, all to make sure the truck survives in the toughest conditions.
And this all raises a really interesting question for the future. We focused on the 400-volt platform, which is the current state of the art, but the next structural revolution is already on the horizon.
What's that next step?
The move to 800-volt architecture. Higher voltage means lower current for the same power. And that means you can use thinner, lighter copper cables. You save weight on the wiring, the harnesses, the cooling. At the same time, solid-state batteries are getting closer, promising energy densities that could cut the battery pack's weight in half.
So if today's engineers are celebrating clawing back 60% of the weight penalty, the engineers of tomorrow might be handed a huge weight saving for free.
Exactly. So here's the thought to leave you with. When that next wave of technology gives you a gift of, say, 500 free kilograms, how do you decide where to spend it?
Do you just give it all to payload for more profit? Or do you invest in a more comfortable cab for the driver, more durability? Or do you use it to enable even cheaper, lighter materials in the structure itself?
That ongoing cycle of technology pushing the limits of structure, that defines modern vehicle engineering. And that's the ultimate challenge. When technology gives you a surplus, what's the smartest way to invest it for the customer?
A fascinating thought to mull over, and a perfect place to end. Thank you for joining us for the deep dive. We hope you feel thoroughly well informed.